Dear fellow scholars, this is a new episode with a special guest. Today we are going to find out how quantum computing and AI can help each other, and we will explore some recent amazing progress in this area. You see, artificial intelligence techniques that work well for one problem usually do not work well for other problems. For instance, some techniques are great for images, but not for text, and others are good for text, but not for molecules or other data types. And also, many of these techniques require vast amounts of computation and are therefore not feasible for large real-world applications. But it gets even worse. The training of these AI models usually requires so much computation that we don't even dare to use them for scientific problems where the available data is scarce. So how could we possibly make AI techniques applicable to scientific computing? This is a question that really keeps me up at night, and I am sure many of you fellow scholars have similar worries. So today, I am absolutely delighted to have a world expert here who has been working on the synergy between quantum computing and AI for a long time. Yes, I am talking about none other than the inventor of quantum support vector machines and neural networks, the great Professor Peter Wittek. Peter, welcome to the channel. Thank you. It's an honor to be here. And now let's have a look at two incredible papers which I believe will put a big smile on your face, just like me. Both papers appeared in Nature just a few days ago. That is truly remarkable. Now, the first paper is exactly what I have been looking for all my career. It is called Quantum Machine Learning with Variational Quantum Eigensolvers, and it proposes an amazing approach to make up for the lack of data in scientific computing. For instance, consider drug discovery. Here we have the molecules on the left and their associated bioactivity on the right. Now, we would like to find new molecules with similar activity to that of a reference molecule, a tamsulosin. We have three major challenges here. 1. We need to understand how the structure of a molecule relates to its activity. 2. We need to be able to find similar molecules quickly. And 3. The data is very scarce. Indeed, experiments are expensive and time-consuming. We don't have that much of them. Now, what does this have to do with quantum computing? Well, the idea is that we can use quantum computers to learn the relation between the structure and the activity, and then use that to predict the activity of new molecules. Sounds good, but how? Well, if you look at the structure of a molecule, we can describe it by a graph. The atoms are the nodes, and the bonds between them are the edges. And then we can ask the quantum computer to find the so-called electronic structure of this molecule. This means that we would like to find the lowest energy configuration of this molecule. Finding the minimum energy state is a famous problem in quantum mechanics. It is called the electronic structure problem. It is notoriously difficult, and often the best we can hope for is an approximate solution. But here comes the twist. The approximate solutions of this problem can be efficiently computed on a quantum computer. This is possible thanks to the VQE algorithm, the so-called variational quantum eigensolver. If you wish, I have a whole video about it. You can watch it here. However, that's still not enough because now we need to relate this electronic structure to the activity of the molecule. And this is done with a machine learning algorithm. In this case, a neural network. And here we go. Here is the beauty of the paper. They propose a system where the inputs of the neural network are the parameters of the VQE algorithm, and the output is the activity of the molecule. Now note that the key observation here is that this system can be trained end to end. That is, the neural network and the VQE algorithm are both optimized together to jointly solve the problem. The result is absolutely spectacular. They show that they can recover the activity of the training data very well. And importantly, and this is the punchline, this method generalizes well to new data. This means that it can handle new molecules that it has never seen before. And the comparison with previous techniques is absolutely stunning. Look here on the left, we have the previous best technique. On the right, we have the new proposed method. And you see that this new method is more than 10 times faster. Wow, what a time to be alive. And get this, they were not only able to reproduce the experiment of Tamsoson, but they could also design entirely new molecules with desired properties. Here is the graph neural network part of the system. Here is the VQE algorithm, and together they form this beautiful hybrid quantum classical system. My goodness, what a beautiful paper, and I believe that this will open up a whole new field of research and applications. The second paper is also excellent, and it is very closely related to this other paper that you see here. And no, it is not a self-reference. It is truly another great work, and it is another quantum-enhanced machine learning technique. However, in this case, it is used for something completely different. You see, in the first paper, we had a graph neural network. These are the nodes and these are the edges, and the task was to find the electronic structure of this molecule. This is also known as the nodal analysis. However, sometimes instead of the nodal analysis, we would like to have the edge information. And for that, we need an edge representation. And this is the task of this paper. The question is, how can we obtain an efficient quantum algorithm for this task? Now I am going to skip the details, but if you are interested, again, there is a video about this algorithm. Here is the quantum algorithm, and here is its classical counterpart. Then they compare the two, and look, the quantum version is exponentially faster. Why is that? Because the number of operations of the quantum algorithm scales only linearly with the size of the molecule, whereas the classical one scales exponentially. So for larger molecules, the quantum algorithm is vastly superior. But wait, this still doesn't tell us how to extract the relevant information from the output of this algorithm. And this is the role of machine learning. Once again, a neural network is used for that, and after training, this is the result. The proposed method is highly accurate and significantly faster than previous techniques. What I also liked a lot is that they tested the algorithm on real experimental data, and it worked extremely well. I mean, look, this is the measurement error of the experiment. This is the proposed method, and look, it is almost indistinguishable from the exact solution. And all this to say that these two new works are very closely related. One starts from a graph neural network and uses the VQE algorithm to enhance its performance. The other one uses the Q-node algorithm to obtain the edge information and enhances it with a neural network. Together they form a beautiful hybrid quantum classical system. But wait, we still need to extract the information from the outputs of these quantum algorithms, and this is where machine learning comes into play, and hence the synergy between quantum computing and machine learning. In summary, I am absolutely delighted to see that these two fields are coming together and really complement each other so well. Quantum computers can provide the missing acceleration that classical AI algorithms often lack. And in return, AI algorithms can help us interpret the results of quantum computations and make them more efficient. I am really looking forward to seeing what else we can achieve together. I hope this gave you some ideas too. If you are looking for a quantum computing course, subscribe if you wish to see more videos like this. And for now, let the experiments begin.